All right. Well, I'll introduce myself first. I'm Stephen Pestana. I'm a graduate student at the University of Washington. And this is the thermal infrared remote sensing of snow tutorial. Um, and so to start off, if you want to follow along, that would be great because I did design this so that it would be interactive and you could follow along. But we're actually just going to first start off on a sort of README document just on the SnowEx Hackweek website. So from the homepage of the website, if you go over to the menu to tutorials, under tutorials, day 3, and then the thermal infrared remote sensing of snow is where we can start. We'll hop over onto the Jupyter lab after going through this a little bit. But first, I kind of want to cover sort of big picture, why do we want to do thermal infrared or why do we want thermal images of snow? We might be interested in seeing when the snow starts to melt. The snow surface temperature can also give us insight into the surface energy balance of the snow, maybe sort of hint at the energy balance going on within the snowpack and the energy exchange with the atmosphere above the snow. And so observations of snow surface temperature could help us maybe evaluate snow energy balance models we'd be interested in. It could also provide context for other thermal or for other remote sensing products like synthetic aperture radar or passive microwave radiometers. And in this tutorial, we're going to look at 2 different types of snow temperature data sets. So we'll look at the evolution of snow temperature over time at a single point. And we'll also look at surface temperatures across Grand Mesa with thermal infrared images taken from an aircraft. And if we have time, we can also bring in an example satellite image. I have a lot of detail in this section and in fact, some links to some other resources about just how thermal infrared remote sensing works. It has some similarities with visible imagery. So you can sort of think of it as you just have a camera, but it also has some tricky parts when we're actually trying to get into measuring temperature rather than just getting a picture. So in short, thermal infrared cameras don't actually give us a direct temperature measurement. Rather, they're providing what we call brightness temperature. So this is the temperature that a surface would be at if it was a perfect emitter of electromagnetic radiation in proportion to its true kinetic temperature. Emissivity is a material property that takes a value between 0 and 1. And that's really what we use to relate the observed brightness temperature with the true kinetic temperature of an object that we're interested in. This is a material property. Luckily for us, for snow has a pretty high emissivity, around 0.98 to 0.99, except when you have coarser grains or you're looking at an odd angle or something like that. So in this tutorial, we're for our purposes, we're just going to treat emissivity as if it's equal to 1 for snow and be looking at brightness temperature and kinetic temperature sort of together. But just a note that that's a piece of the puzzle that you really would have to take into account if you're looking at objects with lower emissivity or if you're expecting your snow to have variable emissivity over time. So I mentioned that we're going to look at a couple different data sources. I'm going to click on this figure just to blow it up here. So on the left, I have our map from the SnowEx 2020 Grand Mesa field campaign, showing all the snow pits labeled with the little text IDs for all the points, and then the flight lines are the red boxes and the black dash boxes. So underneath these flight lines, we actually had a couple sites that were logging temperature continuously rather than at the snow pits where we have just an instantaneous measure of temperature just at one point in time when the pit was being dug. And so today we'll actually look at data from Snow Pit 2S10 where buried underneath the surface was a string of temperature sensors, as well as an infrared radiometer at the surface pointing at the snow. So we have a continuous time series of snow temperature measurements from there. And that was really to provide context for our remote sensing data sets. So mounted on the same aircraft as the SWISAR instrument was a set of thermal infrared cameras. And so these follow these flight lines across the mesa, and we'll be working with mosaic imagery from this. So individual images have been stitched together and projected onto using a DEM so that they're ortho images. But we actually have sort of a time series of these as well. So the aircraft flew on several different days at different times a day. And during each flight, it made several laps around Grand Mesa. And so we can actually capture temperature changes even over a short period of time, as the sun was rising in the morning or something and things were heating up. It also carried a visible imagery camera, which we'll look at to help provide some context for the thermal images. And lastly, if we have time, we'll bring in satellite imagery from Terra, the Aster imager on the Terra satellite. The aircraft flight times were timed so that they'd be coincident with these different satellite data products. And this is one that we can look at where we have a satellite image, airborne imagery, and then our ground data all from the same time. In this tutorial, we'll be looking at February 8th, 2020, when all three of these lined up nicely. If you're interested in more learning resources about sort of the packages we're going to be using, I know Scott and David did a fantastic job going into Xarray and Rio Xarray. There's some more basics for NumPy, as well as more resources specific for the Aster data sets we'll be using. So I'm actually going to hop over to the Jupyter lab now, if you want to follow along. And then maybe before I move on, I'll just pause here if there are any conceptual questions or questions about the data collection that was done at Grand Mesa in 2020 before we start actually pulling it up here. All right, if there are none, we can go ahead and open up the first notebook. So just under the website directory that we've cloned, go into book and then tutorials and thermal IR. The notebook we're going to be looking at today is the thermal IR tutorial notebook. I have extra resources in here. If we have time, we could get into those, or as we can talk about them later. I'm just going to open up this tutorial notebook and close this side panel. So the first thing I have here is we're going to download sample data for this tutorial. So fingers crossed that this works. I have some sample files stored on AWS, and running this command, you shouldn't see any output, but it's storing it in a temporary directory on your Jupyter Lab instance. We'll see below when we open the file that it worked. Next, we're going to import packages that we're going to use in this tutorial. So far this week, you've seen probably NumPy and Pandas. We just heard about Xarray and Rio Xarray packages for the SnowEx SQL database, which was covered already. And then I'm also importing matplotlib to do some plotting. Now, these aren't the interactive plots you saw earlier today, but my challenge to you is to update this tutorial to use all interactive plotting. So we go ahead and import those. And the first thing we're going to want to do is bring in our airborne infrared imagery. And so I have, or what we've just downloaded is a GeoTIFF file. I think I may have accidentally wrote a netcdf file in some, depending on which version of the notebook you have. We're actually going to be opening a geotiff file right now. I have a netcdf file also if you want to look at that. And we're using Xarray and Rio Xarray to with this open Rasterio function. And then we can inspect the contents of the file we just opened. And so again, Xarray gives us this nice way to browse the contents of the file. We see that we have a single band. We see our X and Y dimensions in number of pixels. But for plotting maps of this data, we can look under attributes and see that indeed this geotiff contains transformation information, our coordinate reference system. So we have an EPSG code here already embedded in the metadata, as well as a description of our data set here. We can also look at the coordinate reference system by typing the name of our data set here, .rio.crs, and that'll just print out the same EPSG code. However, you may notice, or maybe not, that this file is in EPSG 32612, which is not the same as the rest of our SnowEx data set, such as on the SnowEx database, which is 26912. So we're going to use the Rasterio reproject function, which was demonstrated earlier today, to overwrite this data set with a new version of itself that's reprojected now into our sort of common SnowEx UTM coordinate system that the other data sets are going to be using, the 26912. We're going to also create just a variable that's a pandas timestamp here. And that's just based on the timestamp from this geotiff file. It's not in the metadata in this file. If we were reading directly from the netcdf, we would be able to grab it from the file's metadata. Here it's just from the file name. And I'm converting this to local time, Mountain Standard Time, when this was taken, so we can compare it with our ground-based data sets, which I have in UTC -7 rather than UTC. So now we can go ahead and plot our infrared image, but what colors do we want to use? I have a little bit of a discussion here about what colors you might want to use, what's intuitive and what's confusing, but most important, make sure to label your color bars so that we know what units we're looking at and what's cold and what's hot. So I'm actually going to use this sort of cool looking, I think it's called magma color bar to make this plot. And so here I'm using the Xarray built-in plotting method, which wraps around matplotlib. So I can do things like set axes labels and put a title on my plot as well. So we can go ahead and run this. And we see a thermal infrared mosaic of Grand Mesa, Colorado. So I'm going to pause here and ask, what do the different colors represent here? You know, what is purple versus orange and yellow, the lighter versus the darker? What do you see in this picture? Does anyone want to try to interpret what we're looking at here?
I can take a crack. So I guess over on the left, that's like off the edge of the mesa. Is that right? So it's warmer and it's at lower elevation. And then way over there on the western edge, that dark purple bit is in the open. So it's colder. Is that right? I'll stop there.
Yeah, that sounds about right. Anyone else see anything interesting here?
It looks like some tree canopies.
Yeah, so, yeah, we do see, down slope off the edge of the mesa, it's warmer. We get up on top, here's the edge of the mesa, have this nice uniform, cold, probably snow. I mean, it's, -5 degrees or something Celsius. And then we get these sort of blotchy, warm areas. We can see on our scale bar here, we have several kilometers across, because these are in meters, these units, UTM units. So we have these large, hundreds of meters forested areas, or what we think are forested areas. And then as we move further east, we also have this very cold region. It's almost black here. So what might that be? Maybe if we bring in a visible image, it'll help us. So we've also downloaded with the sample data a visible image that was taken at the same time from the aircraft, a mosaic of visible imagery. So we can again use the open Rasterio to open a geotiff of that. Again, reproject it into our common coordinate system so that we can plot our data sets together. We can see what this looks like. It's also a single band image. It's not red, green, blue, so it's a black and white image. I forget which band I pulled out. It might be red that I pulled out for this example. And now we can plot these together. So again, we have our airborne IR plot, some options for colors and labels, and then airborne viz plot. We're going to just do that in black and white or in grays. I'm also setting different axes limits to kind of zoom in. So here's our infrared, and there's our visible. Now, what do we think about our interpretation?
Yeah, it looks like a little bit of a low cloud interfering.
Yeah, so that's an important note for thermal infrared. Even though we're not dealing with visible light, we still can't see through clouds, can't see through trees. We're seeing the top of this little cloud here. So hopefully that was familiar to all of you, using X-ray and Rio X-ray to bring in those images. Now we're going to bring in some of the snow pit temperature data. This is from this snow pit where we buried some temperature sensors and set up this infrared radiometer at the snow surface. I have a note here about, what are sort of the differences we might expect to see between the temperature measured at the single snow pit here versus in those images that we just saw, the thermal images. I put down some ideas about what differences there might be. Our ground-based radiometer was looking pointed at a 45-degree angle at the snow versus our airborne infrared camera is looking straight down. And we know that emissivity has an angular component we might have to worry about. Our different infrared sensors, whether the radiometer or the camera or even the satellite Aster image, they have different wavelengths that they're sensitive to. So actually our radiometer and the airborne camera are both broadband infrared. So they're sensitive to wavelengths between 8 and 14 microns. Whereas the Aster satellite image we'll pull in later has multiple thermal infrared bands, and the one we'll look at is actually just around 11 microns. So it's much narrower. We also have to think about, we have different atmospheric path lengths. Water vapor will absorb infrared emitted by the surface, or we could have clouds in our way. So, what's the difference between the path from this radiometer pointing straight down at the snow next to it versus the airplane, which is about 1 kilometer up, versus the satellite all the way up above the atmosphere. And then we also have to consider, this radiometer is measuring a spot on the ground versus what is our pixel size in our various thermal images. From the aircraft, it's about 5 meters per pixel. From a satellite, Aster is 90 meter, but other satellites like MODIS get up to kilometer size. So just some things to think about as we move forward here. The first thing we can do here, though, is we want to visualize, where is this snow pit that I'm talking about in context of this image, of the thermal images we have. So we can connect to our SnowEx SQL database and query the database. Here I'm querying the site data table, and I'm going to apply a filter looking for site ID 2S10. That's the snow pit where these instruments were installed. And then using the function to convert it, the query result to GeoPandas data frame. So we've returned a single row from the site data table for site ID 2S10. We can just double check the coordinate system of the data that was returned. Again, so we see that we're in EPSG 26912, which was our common coordinate system that was chosen. We can look at the geometry of this data frame, which we see is just a point, and those are the coordinates. And now finally, we can plot our airborne infrared image, but this time also add our site data, plot from our site data frame, which has a single point in the data frame. So we can see where exactly this snow pit is in relation to this infrared image mosaic. And it's this red X. So great, this image lines up perfectly. That's why I chose this image. So we can actually zoom in and see, more detail about, this snow pit was out in the open here. I'm just changing the set xlim and set ylim values on this plot. So I just did this manually by looking at the scales here. Again, if someone makes an interactive plot of this, that would be great.
Stephen, can I ask a quick question?
Yeah.
Apologies if I missed it, but with the on-ground sensor, was that configured or designed such that you're getting approximately a 1 pixel area from these airborne sensors that you're comparing against?
No, I would have had to mount it higher. So the spot size was maybe about 1 meter that the radiometer was seeing, whereas the airborne imagery, so now we've zoomed in here, is about a 5 meter pixel. So I'm still getting sub-pixel at that level. So yeah, here we've just zoomed in more to that area. But now let's actually get the data from this point and compare it to the airborne image to see how we did there and how that compares. The data set, so this is the time series data, not the pit data. So the pit data is available through the SnowEx SQL database. So we could also pull that in. But right now, I'm going to be pulling in the time series data from the sensors that were set up there for about a week. They're all available on NSIDC, but we've already downloaded an example or a snippet of that. The raw data needs a little bit of cleanup before we can plot it. And so the first thing we should do is read the files, the Readme file for this data set. And so this command is actually just going to print out the Readme file. So you can read about this. And what we're actually going to be looking at is this Grand Mesa 1 site. And so it describes what was measured there, how it was measured, dates, times. But what we want here are the column names. And we'll when we read in the data set, we'll set our columns to have these names. So here I've just copied those column names into this list. And then we'll use the pandas read CSV function. Since this is a text file, the data file is just a text file that we want to read. But we're going to specify that header equals none. The file does not have its own column headers. And we will then specify names equals column headers. Column headers is this list we created here. So we're just saying the file doesn't have its own column headers. I'm providing some custom ones here. And so when we read that file, we get a spreadsheet thing looking like this with all our different values There are a couple other steps here to clean up the date time values, since the circa 1991 Campbell Scientific Data Logger we use has some funny ways of recording time values. So this should run through smoothly and convert dates into a more pandas Python friendly format. And in the end, we should now see an index that is a pandas date or timestamp object. So now that we have our data formatted nicely for working in Python with pandas, we can go ahead and plot this. And so I'm using the built-in plot methods that pandas has. So I specify my data frame, which I just called df. I'm going to plot radiometer average. So this was the average temperature measured by the radiometer over a 5-minute period. Give it some styling and format my axes and add some labels and a plot title. So here we go. We have our snow surface temperature data for about a week out on Grand Mesa. If you want to see what the subsurface looked like from the other sensors, we can copy this code snippet here. I'll just do that right now. I think I have to click in here to copy this. I just double clicked on this cell to edit it and then copied that. Go up here and add these. I put this in here because I already picked out some colors for it and some labels, so we can plot that again. And so now we have in black, again, the snow surface temperature, and in blue, temperature at different depths, with the darker blue, being at 30 centimeters below the snow surface here. There was a question I saw, the little spikes at midnight.
I might be seeing it wrong, but
let me see. Let me do this again.
it shows up just, there, like the first line.
Oh yeah, I see that. I suspect maybe my time conversion did something odd. I remember one of the things in here is, I think the data logger recorded midnight as, oh yeah, here it is. Changed midnight from 2400 to 00. So it's probably in here somewhere. I might be accidentally moving values around that I shouldn't be. So
Well, got it.
Yeah, I'll have to look into that and do some more QC on this data set. Again, this is the raw data, so we're trying to do some QC here ourselves. Here, the second plot, I've just added xlim with some timestamps to zoom in just on February 8th. So the day where we have the IR image that we pulled in earlier. So now that we're able to pull in the thermal infrared image and the ground data that we know is smack dab in the middle of our image, let's try to compare them against each other. So to pull out the temperature value at our point that we were able to plot on our image, we can use the Rasterio clip function, which lets us take a raster and then essentially select at a given point, given some GeoPandas geometry, what is the value at that point? This is a pretty powerful tool. In one line, I can pull out what is the temperature in, or what is the value from our airborne IR image at our site data frame point, looking at the geometry there. What this does, the clip function does is, well, it clips your raster. So it provides a raster image back to us. But because we just specified a single point, it returns a single pixel. So we have our dimensions of this data array that returns as one band, one Y value, one X value. And we can actually see the value here is -5 degrees at that single point. But again, the question is, this is a 5 meter or 5 by 5 meter pixel. And we're trying to compare, a about 1 meter spot from the radiometer to that pixel. But then there's also the question of, do we actually know where that 5 by 5 meter pixel is? The aircraft data, looking at it in other contexts, we've decided it has maybe 10 or 15 meters of geolocation accuracy. So we don't actually know that it's like that specific pixel lines up with that point. So instead, what we can do is we can add a buffer around our point to clip our raster to a larger area to maybe take some of that into account. I did say the airborne imagery has maybe 15 meter geolocation accuracy. I go way overboard here and I just say, let's put a 200 meter circle, so 100 meter radius around our point, and let's just look at all the temperatures in that area and see what those look like and how those compare to our ground data. So I'm using this buffer function here on our GeoPandas data frame and giving it a 100 meter buffer. A good thing about working in UTM coordinates is I can just put in a 100 here because our coordinate system is already in meters, UTM's in meters. So I don't have to convert to degrees or arc minutes or whatever. And we can preview the geometry we get out of this buffer. So we went from a point to now we have a polygon. So this is a circle around our point. And we can plot this along with our airborne infrared image, the single point location of our snow pit, and then the buffer circle around our location. So here we go. It's the same image, same point, but now we drew this circle around our point. And we can again use Rasterio's clip function, but now with our buffer geometry, which is this polygon. And the result again is a data array, but now it is 40 by 40 pixels that fit into this area. And we can plot that. So what do we see here? Well, first of all, note that I changed the color bar values. Originally, I had the color scale going from -10 to +10 degrees Celsius. Because we're looking at such a uniform area, I was sort of interested in what is the variability here. So I zoomed into -7 to -4, sort of centered around 5.5, where I thought the temperatures would be. I've also created a histogram here of all the temperatures within this area and plotted a couple vertical lines. One showing the value of that central pixel, which is the cyan or bluish green line here, versus the mean value for that whole area. So kind of a question can be, is the center of this circle really representative of the whole circle? It doesn't look like it. It looks like it's a little bit warmer than this, 200 meter diameter area. Now that's a pretty big area, so we could realistically we'd make this smaller, like I said, 15 meters or something. And if you want to see an application of essentially all of this, check out Lundquist et al. 2018, which essentially did this with MODIS imagery and airborne imagery in Yosemite National Park. How are we doing for time? All right, we can wrap up the airborne imagery part. So the last thing we want to do here is take the airborne imagery in this circle and plot it on our time series chart of the ground-based data that we had observed there. So here, this is similar to the plot we had earlier, where I'm plotting the average radiometer temperature for every 5-minute period. at our ground-based site, I'm going to plot the mean airborne infrared temperature for the whole clipped area around in that buffered circle. And then I'm also going to add an error bar that just looks at the minimum and maximum temperatures in that circle, just to get like an idea of the range of temperatures in this whole area and how it compares to what was measured on the ground there. So we end up with this. That's pretty interesting that, you know, our airborne image, you know, captured a mean that was a little bit warmer than our radiometer did on the ground there. But our radiometer on the ground is still in the range of values that the airborne infrared image captured. So I can also pause here and see if there are questions. The last part of this, which I wasn't sure if we'd get to or not, we just have a few minutes left, is bringing in the satellite image. It's more or less the same process. We're using the same tools, Rio X-Array, clipping with geometry, doing some comparisons. And then I do a reproject match demonstration at the end. Are there any questions right now before we zip through the end? All right. So those airborne infrared mosaics were timed to be collected at the same time as the NASA's Terra satellite was passing overhead, and the Aster instrument can get us 90-meter resolution thermal images. So we can load in this image and see that it is quite a bit lower resolution. We only have, you know, 800 by 900 pixels here. It is actually covering a much bigger area. So when we plot that, we'll be able to see. But I'm also going to change its coordinate reference system to our common EPSG 26912, which we're using for the SnowEx data sets. So again, I use the Rio reproject here. I'm going to create a timestamp for our image to use later. And doing just a quick plot, we can see Grand Mesa is just this small little thing in the center of our image. So this image is really big. It covers a much bigger area than our aircraft even flew over. Now I haven't done any styling of this plot. This is just how X-Ray is plotting it by default, but we can see the color bar here that's labeled, you know, these values looks kind of strange. So we have 0 all the way to 1750. What is that? What do these values mean? This is when you really need to dive into product documentation and sort of the user guides for the Aster data. What these values are is they're the digital numbers. They're just how they scale and store the data values. So they have no physical meaning, but there is a way to convert them into physical units, which you can learn all about reading product documentation. But I have written a couple functions here to convert these digital numbers into radiance, and then from radiance into brightness temperature. So we can go ahead and just run these and convert it for this band. During the unit conversion, it, for some reason, drops the coordinate reference system. So here I just add it back again, and then we can plot, finally, a temperature map. We got lucky here in that we had an aircraft fly over and leave a contrail across our scene, but it is not over our study site on the Western Mesa. So we got lucky. That's what this linear feature is, just a thin cloud behind an airplane there. So next we can plot together our Aster image and the airborne image to see what they look like side by side, and we'll zoom in on Western Grand Mesa. Most of the code you're seeing on these is just I'm styling the plots. And because I'm using matplotlib, I'm, I guess, having to do it a little bit more manually than with some of the other fancy plotting utilities. So here we are. Here's our airborne infrared mosaic and our little snow pit site here. And here's our Aster image and the same snow pit site. So you can just see by this quick inspection the resolution difference we have between these two images. Another plot just zooming in. What we'll do then is the same Rasterio or the Rio X-ray clipping function. Yeah, here we are, just zoomed in. You can sort of make out the actual pixels in the Aster image here compared to the airborne image. You still can't see the individual pixels. We'll do the same Rio X-ray clip of our point, this red X, as well as the buffered area, the red circle, from the Aster imagery. And when we plot that, just zoomed into that buffered area and also try to plot a histogram, we can see that we've only grabbed 4 pixels. Also, something to note here is that it looks like it's grabbing pixels that the top left corner of the pixel is within the circle. There are other options for these, for the clip function, such as any pixel that overlaps the circle. I didn't set those options. This is just the default. So that's something to note, that we're actually excluding a lot of area that we might be interested in because it's only looking at pixels that the top left coordinate is inside the circle. We can also look at those 4 pixel temperatures and plot them on our time series here. And these ones actually match up pretty well with our ground data, but that's the greatest scale difference. We have a small point versus, 90-meter pixels. Somehow that matches better than our more detailed data, which kind of shows more of the variability across the site. And then this, which is what I called the bonus activity, is using the reproject match function to reproject the airborne imagery from 5-meter resolution into 90-meter pixels. And here, instead of using the nearest neighbor, which is the default for the resampling, I set it to option 5, which is to take the average within every 90-meter pixel. And I'll just run through this quickly and plot the result. So this is similar to what we saw with the DEMs. I will then take the difference between these two, so we can see if there are patterns between the two, where they agree and where they disagree. I'll just run all these, so it takes a second. I think we're just about out of time right now. And I think it's supposed to head into break after this. So if I can take questions or.
So Stephen, you had a couple questions about the error message. You went over real fast. They said, don't worry, it doesn't matter. And people were curious why it was there.
Yeah, which error message was that? I remember.
Yeah.
Oh, it's because I'm using in the conversion from radiance to brightness temperature, I'm taking the logarithm, and I have no data values. So essentially I have nans in there, and it doesn't know what to do with those. And so it's saying it is encountered an invalid value, that it's trying to take the log of no data. I think there's probably a cleaner way to do it so that you can tell it to ignore those and not give you a warning. But I think that's what's going on there.
I only see compliments in the chat that I'll let other people talk.
I have one question. So which source do you trust the most? The on-ground sensor measurement?
Yes, because I put that there myself. I mean, those, yeah, I mean, that is what we're, considering our ground truth. It's, about as close as you can get to ground truth is going there and measuring the temperature yourself. Like kind of like with the snow pits, all those temperature measurements, those were made with STEM thermometers put into the snow. What else can you do besides that? When you get to these satellite data products, the Aster product, there are a lot of pretty complex algorithms going into that. So assumptions having to be made. I mean, I'm not looking at a land surface temperature product here. This is just brightness temperature. So we haven't taken into account emissivity. But there are a lot of smart people who develop those products. So those are probably pretty good. I think we have more questions about the airborne infrared images. Just that they are, they're pretty raw data sets. And so we want to use these, but we also need to be careful about how exactly we use them, because they're sort of custom and more
Can
raw.
I comment?
Yeah.
So basically, the thing you have to always keep in mind with thermal measurements is that what it's trying to sense is temperature is influenced by the temperature of the instrument itself. And so the instruments, the camera, the point sensor, any thermal instrument is always trying to correct for its own temperature as opposed to its target temperature. You'll get more error when there's a greater difference. So for example, when we fly the aircraft in warm air over cold snow, you'll get more error because there's a greater difference. In terms of absolute value, Aster actually tends to do the best because the instrument is in space. And so it actually can calibrate to a really known temperature, and it's not changing. It's just super, super cold out there, and it doesn't have influence of another temperature. Drones tend to have the biggest problem in terms of calibrating, and Stephen has a nice paper looking at like drift in drones and thermal temperature. So you have both the absolute value, where Aster probably is set to absolute, but then you have resolution issues where Aster is always blurring things, and often blurring things give you more error than the absolute temperature difference, if that makes sense. So they're true in sort of different ways.
Yeah, that makes a lot of sense. I think, I guess my follow-up question was, we're in the airborne thermal infrared, we're seeing a lot of variability around that one point. And so if we have a ground-based measurement that is, at a single point, how representative is that of the area around that point that we are able to sample with the thermal infrared?
Yeah, I think that's an outstanding question, and that's what I'm trying to look at with this example here, is that there is variability. I think that variability is real. I mean, if you squint at this, and if you had seen, or I guess we could also bring in the visible imagery, or if you were there or saw pictures, there are snow drifts. The snow drifts are causing little shadows. They're receiving different amounts of sunlight. And so they're heating up at different rates. It was also really windy. And so I'm sure there were a lot of atmospheric controls on snow temperature there. So when I see this sort of like zoomed in and stretched color bar plot, I think, yeah, those could be different temperature differences because of these different snow drifts. However, in other places, if you look at the airborne imagery, you'll see things like striping, which, that's, not a natural looking feature. You see it across images in different areas, and then you can kind of realize, okay, this is something in the camera itself. It's causing these stripes, or the edges of the images are always colder than the center. There's sort of like this bias across the image detector itself.
That's tricky, yeah. So it seems like the error isn't consistent all the time. I was thinking if one could use the ground-based point measurement to calibrate the rest of the thermal IR grid, right? So the difference at that one point between the thermal IR and the ground-based measurement, and maybe that offset is consistent all throughout, but maybe not. if we're
Yeah,
seeing
the-
that striping. I don't know.
Yeah, that would be called like a single point calibration, where you just kind of shift everything to meet that single point. But the trick is the radiance that the camera is actually sensing. This like Stefan Boltzmann's law, the emitted radiance is proportional to temperature to the 4th power. So it's not linear. If you want to be a little bit more careful, you could have more than one point of calibration. So maybe like pick a cold area and pick a warm area, so that rather than just shifting your temperatures up and down, you can kind of try to fit them to like a couple different known temperatures, which I think is what, a lot of folks doing drone thermal imagery, like Jeremy is here, I think he was on the Mesa doing some of that. Where you're trying to calibrate with just more than one point, but that's what we have here. It would be interesting to look at more points across the Mesa and see how those all compare.
Awesome, thank you.
Stephen, with the aerial images, were there like ground targets, set up ground control points to, when you're doing the ortho image, try and estimate that geolocation accuracy or get it more pinned down?
No, we didn't use anything like that. But I'm thinking, so essentially because the aircraft has a GPS INS on it, so it should know its orientation and location, somewhat. We didn't set up anything on the ground, but I think you
can
could
match
probably
trees.
use some natural geolocation points. I mean, there's an antenna farm out there as well, and some fence lines that you could probably see.
I looked at it in the Tuolumne data set, and based on like just matching individual trees, there tend to be about 2 to 3 meters just uncertainty. But if you aggregate, the reason why the airborne is in 5 meters is that 5 meters, it's pretty correct. If you start looking at it at 1 to 2 meters, then it shifts around slightly. And so particularly in something like if you're at the edge of trees and you're trying to correct it with a point, your geolocation accuracy can really be quite off. So we started just picking little, circles around the point to assume we know it's somewhere in here.
Gotcha. Okay. Yeah. And I remember with Aster working with it back in the day as well, many pixel shifts and looking at natural features like lakes to try and align those images better.
I don't see anything more in the chat other than saying thank you, Stephen. So I think we could give a virtual round of applause.
Thanks.
Anthony will help here.
If you're interested in this more, there are bonus notebooks in there and some other scripts that I encourage you to check out.
There was one question if you had any of the ghost ones in there.
Not in here.
Not in here,
but if you're really interested, then we can talk about that.
Thank you.
Thank you.
Thanks, Stephen. I think we can stop recording, Scott.